Okay, 5.1, organized counting with Venn diagrams. So looking at Venn diagrams, what is a Venn diagram? Okay, Venn diagrams are used to organize information for situations in which the number of items in a group are important, but the order is not important. Okay, so they are displayed by one or more circles in a rectangular box. For the scope of this course, it's going to be 1 to 3 circles, usually only 2 or 3. Okay. And when I talk about elements, what all that means is the items in the set. So example, the elements in this set of numbers from 1 to 5 are 1, 2, 3, 4, and 5. Okay, those are all the elements. And when we talk about common elements are items when items are in 2 different sets in the Venn diagram. So this is going to be shown with like an overlap of these circles. Okay, so we would have circle A, circle B, and then in the middle here would be the common elements, which is all the items in A and in B. Okay, so that's the overlap. Okay, so let's do an example. There are 12 students on a soccer team, 16 on a baseball team. Okay, so we're talking about 2 teams here, soccer and baseball. When planning a tournament with both teams, the coach has to arrange transportation for a total of 20 students. So what this 20 means is that like the total students is 20. So 12 play soccer, 16 play baseball, but if you add those together, you might be thinking, okay, well, this doesn't add up to 20, so what's the difference? Okay, so let's make a Venn diagram to see what the overlap would be, okay? So we would have a box, and what this box represents is every element in all of the sets that we're talking about. Okay, I'm going to go ahead and draw 2 circles. And the reason why I'm drawing 2 circles is this circle is going to be the number of people on the soccer team. And then this circle is going to be the number of people on the baseball team. If you have a number here, that would be like the leftover students who are not on the soccer or the baseball team. Okay, that is not going to be a part of this question because for the scope of this question, we're just talking about the 20 students. Okay, so if 12 are on the soccer team and 16 are on the baseball team, you can do this in kind of like a logic way. So like 12 and 16. But if 2 are on, if 1's common, then it would be like 1 and 15, right? Because then 12 and 16. If 2 students are common, it would be 10 and 14. Okay, and again, this is still over 20. Okay, so you'd have to keep going like 3. So this would be like 9 plus 3 would be on soccer, and then 3 plus 13 would be on baseball. Okay, soccer always has to add up to 12. Baseball always needs to add up to 16. Okay, so let's keep going. 4, so that 8 and 12, so that's too many. 5 in the middle would bring us to 7. So 7 and 5, and then 11. Okay, so you can pattern like this, and we're gonna see a way that we can actually do this better. So 7, this would be 6 and 6 would be 12, and then 10 and 6 would be 16. So now we're at 22. Okay, what about 7 students? This would be 5. This would be 9. 5, 7, 9. It's 21. Okay, so then we would pattern down to the 8. Okay, 8 and 4 would be on the soccer team, which is 12. And then 8 and 8 would be on the baseball team. So that's what we would get. Okay, algebraically, there's a way easier way of doing this, but I just wanted to show you guys that you can pattern, and that's what we'd be doing. So that middle number here would be the elements or the students on both teams. So we double counted them. So in the 12 plus 16, the reason, and this kind of blends into B, explain why you cannot use the additive counting principle to find the total number of students on the teams. If we took 12 plus 16, we already talked about this, that would be 28, but that wouldn't make sense because there's only 20. Okay, we cannot use it because there are students who overlap. So, or slash are on both teams. Okay, but just because they're on both teams doesn't mean that they need 2 seats on the bus. Okay, they do not count as 2 people. They still only count as 1 person. Okay, I'm going to show you how to do this algebraically, okay? So this is just kind of like a basis of what a Venn diagram is and how we set it up. Now, if we had all these numbers, I'm going to draw a Venn diagram, and this is going to be completely separate, okay? So what I would draw is I'd say to myself, okay, there are X number of students that are on both the soccer team and the baseball team, but we don't know what that X is. But the way we get the number in this circle is by doing the 12 minus whatever's in here. So we know this entire circle is going to add up to 12. So if we take 12 minus x and then add x, that's going to equal 12. Now, in the baseball circle, it's going to be 16 minus x. Okay, we know that 16 people are on the baseball team, but then we're going to subtract x because with this circle, it only takes into account here, not the overlap. Then we're going to add the overlap. So algebraically, if we want to add these 3 up, we know that the total number of people on the bus is 20. So we're going to go 12 minus x plus 16 minus x, and that's going to equal 20. Okay, 12 plus 16 is 28. Negative x plus x cancel. And then we have, negative x equals 20. So let's bring the negative x over. It'll become positive x. Bring that 20 over. It becomes negative 20. So 28 minus 20 is 8. So if you want to do this algebraically, which is eventually where we're going to be at, this x equals 8 will go in the middle. And then to solve for this, we do like 12 minus x, which is 12 minus 8. And we get 4, and that's how we get 4 for this circle. And then for this one, we'd be 16 minus x, which is 16 minus 8, which is 8. And that's how we get 8 for that circle. Okay, and C, determine how many students are on both teams. So for C, 8 students are on both teams. Okay, and D, determine the number of students in the remaining regions of your diagram and explain what these regions represent. Okay, so for this region here, I want to highlight this in green. So this region here, there are 4 students. So this means 4 students, I'll put this a little darker. So 4 students play soccer only. Okay, and then if we take a look at this region, and let me do this with maybe like a pink. Okay, if we look at this region, like without the x, without the overlap, this region here, we can say 8 students play baseball only. And that's what those regions mean. Okay, number of elements in a set. So the number of elements in set A is represented by this notation. So it's just like the number in A. That's how it's so lowercase n and then uppercase for the set. Okay, and then we have union and intersection, and these guys go hand in hand. Okay, so the union is all the elements in either set A or set B. Okay, so this is an important word when we get to word problems, because if it says this set or this set, then it means one or the other, or both, or not both. It could just be in one, and that's okay. So it's like everything. So this is just one of the free-for-alls. Okay, it's also represented by like a U, but it's not like a U like this, as it doesn't have that part there. It's a U symbol, so A or B. Now, intersection is more restrictive. This is all the elements in both sets A and in set B. And this is called intersection. And if you're thinking about the N, intersection, it's A and B. Okay, again, when we're doing word problems and we're reading and the question says and instead of or, we're looking for that intersection. We're looking for this overlap. So if you want to write overlap here, that will help. Okay, and now what we basically did in the previous question is we basically used the principle of inclusion and exclusion of two sets. So what this means is that for sets A and sets B, say we had like X, Y, and Z, okay? We can't just add up everything in A and then everything in B, because what will actually happen is we're going to be double counting that Y value. We're going to be double counting that overlap. So the principle of inclusion and exclusion states for sets A and B, the total number of elements in either A or B, right? So just like all of them, is going to be the total number of elements in A, which is like X plus Y, plus the total number of elements in B, which is Y plus Z. And then we're going to subtract that middle number because we double counted it. So we're going to subtract the number of elements in A and B. So let's take a look. Okay, example 2, applying the principle of inclusion and exclusion. A drama club is putting on 2 plays. There's 11 actors in the first play and 15 actors in the second play. Okay, so let's go let A represent the first play. And we're going to go let B represent the second play, just so that we can mark the Venn diagram with first and second. Okay, so if you think about this as a Venn diagram, we're thinking A, B, okay, and A says if 3 actors are in both plays, how many actors are there in all? So 3 actors are in both plays. So for the first play, it's going to be 11 minus 3, which is 8. And then for the second play, so the number in A equals, okay, the number in B is going to equal all 15 actors minus the 3. So we're going to get 12 in the second play. Okay, so we can either go like the number of actors in A or B is going to be the number of actors in A plus the number of actors in B minus the number of actors in A and B. Okay, so if we go from the original, so we can see it in the Venn diagram, but if we want to go algebraically from the original, we're going to go 11 plus 15 minus 3. And we're going to get 23. So there's 23 actors in total. Now, referring back to our Venn diagram at the side, if we added 8 plus 3 plus 12, we also get 23. Okay, example B. Use a Venn diagram to calculate how many students are in only one of the two plays. So what we're going to do is so I want to show you some like spin-offs of this notation. So the number of people in only one play equals the number of people in only the first, or only the first play, plus the number of people in only the second play. So you can also write it out like that, and that's totally proper notation. Okay, so only the first would be 8, only the second would be 12, so that's 20 people. So 20 people, PPL, are in only one play. All right, example 3, working with 3 sets. So of the 140 students at Maxville High School, I'm going to list these. 52 are taking advanced functions. 71 are taking data management, and 40 are taking calculus. Okay, so those are all individual. So I like separate these and I write them in order. So all of these are just individual stats for like the full circle. Now, 15 of the students are taking advanced functions, are also taking data. So 15 are advanced functions and data management. And I put this sign because that's an intersection sign. Okay, 8 students who are taking data are also taking calc. So 8 is data management and calc. And 11 students who are taking calc are also taking functions. So 11 is advanced functions and calc. And it doesn't matter if you put calc and advanced functions or vice versa. Okay, so those are my 3 intersection parts. Now, 2 students are taking all 3 courses. So that's actually advanced functions and data management and calc. And yes, this double intersection extends it so that these 2 people are in all 3 of these circles. Now, let's make a huge Venn diagram. Okay, we're going to have 3 circles. Okay, we're going to name this one advanced functions, this one data management, and this one calc. Okay, and we want to work from the inside out. So 2 people are taking all 3. So I'm going to put that 2 right in the middle. This middle part is going to be the intersection of all 3. Now, let's just work upwards. Advanced functions and calculus. So advanced functions and calc. So that's this entire circle. But here's the problem. We already have 2 allotted in there. So if we have 11, it's going to actually be 11 minus 2. So this is going to be 9. Because that's going to be all 11 are taking advanced functions and calc. Now, next one, data management and calc. So data management and calc overlap here, but there's already 2 people allotted for. So we wouldn't put the full 8 in here. We would do the 8 minus 2. So we're going to put the 6 in there, which still adds up to 8. Okay, and advanced functions and data management is going to be overlapped here. Okay, again, we already took into account 2 people. So we're going to go 15 minus 2 is 13. So 13 people are going to be in this part of the Venn diagram. Okay, so let's extend this to individuals who are only taking one of the 3 courses. So there are 40 students taking calculus. That means for this entire calculus circle, it has to add up to 40. So we already took into account 9 people who are taking only advanced functions in calc, 2 people who are taking all 3, and 6 people who are taking calc and data. So what we want to do is we want to do the 40 and we want to subtract all of those because we already took them into account. Okay, so that will be 23. So 23 students are only taking calculus, no other maths. Okay, let's do the next one, data management. So the data management circle, let's do this in green. The data management circle is this big, and there has to be 40 students in there. Oh, sorry, 71 students in there. We already took into account 13, 2, and 6 students. So let's subtract 13, 2, and 6. And those will be all the students who are taking more than one course, including data. That leaves us with 49 students only taking data management. Now, advanced functions, 52. So advanced functions is going to be this big, and this entire circle has to add up to 52. So we're going to go ahead and subtract the 13, the 2, and the 9 that have already been accounted for, and we get 28. So 28 students are only taking advanced functions, no other math courses. So B says, it asks us how many students are not taking any of the math courses. So if we reference the original question, it says 140 students are at Mathville High School. Now, if we added all of these up inside the Venn diagram, these are all of the students who are taking math courses. And what I'm doing is I'm just writing out all of these numbers, 28, 13, 2, 9, 23, 6, 49, and I'm just adding them together. This is going to account for all of the students who are taking 1, 2, or all 3 math courses. I get 130. Therefore, if there's 140 students at the school and 130 are taking at least one math course, therefore there are 10 students who are not taking math. And that 10 goes in here at the side. You can box it if you want. It doesn't have to be boxed, but it goes still in the Venn diagram because the entire number of people at the school have to be accounted for because that's the population that we're talking about in there.